Got it? I'll begin. Heavenly Father, we thank you for this morning. Again, Lord, I thank you for these students, for this opportunity we have just to meet together and study your creation. Lord, I just pray that you bless this class. Help us to, again, Lord, glorify you, Lord, in what we do. In your name I pray. Amen. All right, let me just go over an example I did last time. So I'll start on this board over there. Well, maybe I should actually start. Let me start over here for just a second. First things first, I should be clear with you guys. There are some things you need to memorize. There really are some things you need to memorize, right? Like, you should really at this point have, or soon should have memorized that this is the geometric series result, right? Because we're going to use that a lot. You should also memorize the power series for the exponential. This you need to know. All right. You probably should also memorize the power series for hyperbolic cosine and for sine, and also for, right, for, let's see here, cosine. What's the difference? Cosine of u is what? Same formula, right? But with what? Minus 1 to the j. So a lot of this stuff we wrote last time, so you don't have to write it again if you don't want to. But basically I'm advocating the view that you should think about these formulas not just in terms of x, but perhaps in terms of another variable, so that you can free your mind most efficiently to make a substitution. Because a lot of times some of the more interesting problems that I can come up with, which aren't that hard, but look hard, are actually just based on a substitution. You know, setting u equal to something. I'll work some of these as we go on here this morning, but not yet. So that's my first order of business, is just, you know these things. Okay, you should know these things. If you don't know these things yet, that's okay, but don't let that be the case for too much longer. Now, you're like, well, I don't want to memorize these things because I want to be able to derive them. Good, that's even better. But what's a reasonable time frame to derive any one of these facts? The answer is about 1 minute. If it takes you then longer than about a minute to derive any of those, then you're not doing it right. Right? I mean, anybody, given 10 minutes and an understanding of Taylor's theorem, can derive the Taylor series for a function just by successive differentiation, right? But if it takes you 10 minutes to do that, any one of those are not 10 minutes that I'm planning for you in your next exam, right? I want you to be past that point. I want you to understand these, be able to use them. All right. That comment aside, let's look over here. So this is yet another. Last time I showed you guys how to find the power series for inverse tangent using a geometric series technique, remember? This is another geometric series technique trick problem. We're going to find the power series for the natural log of 1 plus x. Okay? How do we do that? Well, I guess you could just use the Taylor's generation. You could just differentiate and plug in 0 or whatever. But I'm gonna show you a different way. Okay, so what I do is I say, okay, well this I can't recognize as geometric series immediately, right? But if I differentiate this, f prime of x, or df dx if you like, that's 1 over 1 plus x, right? And that allows me to convert to a series, because this is the geometric series result, with a equals to 1 and r equals to minus x. There it is. And then I simplify, that's minus 1 to the k times x to the k. Right? Until you've written it like this, it's not a power series. Power series is coefficient times x to the k. Minus x to the k is not a power series. It's something else. The theorems that I'm using, and that will at some point justify, assume that the format of the series is written as like c sub k times x to the k, or x minus c to the k. It's important to rewrite it this way before you do things, okay? That's df dx. Oh man, I don't want df dx as power series. I want f of x as power series, right? So what do I do? how do you undo a derivative? You integrate, right? So I say, okay, well, f of x is equal to some constant plus the integral of df dx, right? But what is that? Well, that's the integral of this series right here, right? How do you integrate a series? Term by term, just polynomial integration, right? So what's the integral of x to the k? It's x to the k plus 1 over k plus 1. The minus 1 to the k is just a constant. It rides along. Ignore it, essentially. Just it rides along. It's a constant with respect to the x integration. And so we get that f of x is equal to some constant plus this series. Now, I want to figure out what exactly is f of x in terms of a power series, right? So I got to deal with this constant. The way to do that is to plug in a value which we already know for the function to try to figure out what the constant has to be. So one thing I have to do is to look at the series. Well, this series is like x minus x squared over 2 and so forth. If you plug in k equal to 0, if you plug in k equal to 1, you get x for the first term, right? Because minus 1 to the 0 is 1, x to the 0 plus 1 is x, divided by 1. The first term is x, the second. And if you go to the next one, you get minus x squared over 2 and so forth. The point is, all the terms in the series I just boxed in red have an x or higher power. So what happens when we plug in x equal to 0? That's the 0 series, right, which we know converges to 0. And then we're left with this constant, right? On the other side, if you plug in 0 into the natural log of 1 plus x, you get the natural log of 1, which is 0. So consequently, the constant must be 0. Basically, both of the examples I've showed you thus far, the constant has more or less been irrelevant. It's worked out to be 0. You might get the impression you could just slop through it and ignore the need to add a constant. Trust me when I tell you, you shouldn't do that. There are examples where if you don't add the constant, you'll get the wrong answer. Not all of them, but it is an important step to add this constant when we integrate. But it's not just like a plain indefinite integration, right? The constant doesn't need to stay in the answer because what we're trying to do is define the power series for a given specific function, right? There's no arbitrary constant in that. The function natural log of 1 plus x has specific values, 1 for each x, right? So the constant will not be in the answer. We're going to be able to pin it down to be a specific value. In this case, 0. All right, fine. So there you go. Natural log of 1 plus x is the sum k equals 0 to infinity of minus 1 to the k over k plus 1 times x to the k plus 1. That is a power series. Well, it's not a, yeah, it's a Maclaurin expansion for the natural log of, Maclaurin series for the natural log of 1 plus x, right? Now, if you go back up to our geometric series step, that made sense for what? Minus 1 less than x less than 1, right? That's where the ratio has magnitude less than 1. Something cool happens. When we integrate, the integral of that series has a larger domain, right? If you plug in, so like the domain of this is actually minus 1 to 1 included. This 1 somehow got included by the integration process. That's kind of neat. We integrated a series. It actually added a point to the end of the domain. So how do I know that that's included? Well, down here in the red, if you put x equals to 1, what do we get? We get minus 1 to the k over k plus 1, 1 to the k plus 1, which is just 1, right? So if you plug in x equals to 1 into the series, we get 1 minus a half plus a third minus a fourth. Hey, we know what that is. That's the alternating harmonic series. We have proved previously that that converges by the alternating series test. That's how I know 1 is in the domain of the series. There is a subtle point here, which is how do I know that the function is actually replicated by the power series at that point? That's a subtle point that will be dealt with by Abel's theorem. Maybe next week. Trust me, it's true, though. You got a question, Travis? Or? Oh, okay. But, you know, something cool, right? Okay, great. 1 converges, and 1 gives us the alternating harmonic series, right? But what happens when you plug 1 into the other side? What is that? 1 plus 1, 2. Yes. So that is why the alternating harmonic series converges to log 2. That's how I knew that. Eh? So if you're keeping score here, we now have another way we can calculate the sum of series. Before this point, how could we calculate the sum of a series? It was geometric, right? Or it was telescoping. Now, we also have this thing we can do. Now we have this other thing we can do, which is to plug in values to known functions and compare them to the series expansion. I already used this on you guys, whether you realize it or not. Earlier lecture, what did I do? I did sine of 1 was what? 1 minus 1 over 3 factorial plus 1 over 5 factorial. Remember that? Well, that's exactly the sum. J equals 0 to infinity minus 1 to the j over 2j plus 1. See what I was doing? I just knew things that you guys didn't know yet, right? Because you haven't had this course yet. But I mean, there's tons of series that I know the value of because I recognize those series as just being the series expansion of a given function whose values I know for reasons of custom, right? Do I really know what sine of 1 is? I mean, you have a familiarity with sine of 1, right? You're used to it. You've worked with it before. But do you really know what sine of 1 is? I don't think you really do, in the sense that you couldn't tell me its value, right? Without picking up a calculator, right? Or in the olden days, you'd have to go to your trig table, right? Because sine and cosine, calling sine and cosine what they are, is just a convention to refer to specific ratios of acute triangles and to categorize, you know, this vast catalog of knowledge we have about the ratios of sides of right triangles and also polar coordinates and all that junk. Now, if you turn the tables on that, right? If you didn't know that stuff and you wanted to define sine, you could actually use this formula to define the sine of u. You could turn the tables. You could say, I'm going to define the function by a power series expansion. In fact, some people do that. The definition of the exponential function. You could take this to be a definition of the exponential function. Check this out. E to the x equals, by definition, the sum, k equals 0 to infinity, of 1 over k factorial x to the k. I personally like this as a definition of the exponential. It's easy to prove from that it has all its basic properties. Like you can prove the derivative of the exponential is the exponential again, and so forth. You can prove all of the standard properties. E to the 0 is 1. Easy to prove. Harder to prove, e to the x times e to the y is equal to e to the x plus y. We'll get back to that some other day. But I'm just telling you guys, there's another way of thinking. You can take series as primary, and you can use them to define things if you want to. This is nice, by the way, because you can use this in more abstract contexts to define exponentials. For example, the matrix exponential is defined in this way. If you want to take the exponential of a matrix, you use the series to define that. Anyway, I digress. Any questions? All right, one more example, and then I'll take your homework questions, okay? I want to look at, find power series expansion of f of x equals to sine x at x equals to 3. In other words, I'm taking the center to be 3. I'm going to show you two ways to do this, all right? I'll first do it the unclever way. Okay, what's the unclever way? The unclever way is just to straight up calculate f of x equals to sine x, right? What's f prime of x? Cosine x, yeah. F prime prime? I said after this I take homework. That's slightly incorrect. There's one example that has to be given as a follow-up to this. Otherwise, I don't really make my point. The third derivative is what? Minus cosine x, right? The fourth derivative? Sine x, right? And then we loop. You make the appropriate sound effect. I don't know. But so what's f of 3 is what? Sine 3, right? F prime of 3, cosine 3, right? F prime prime of 3, minus sine 3, f triple prime. So f3 of 3, cosine of 3, minus cosine of 3, right? f4 of 3, sine 3. Right? Why am I doing this? Because I'm going to use the Taylor's theorem to generate the series for sine at 3. What does Taylor's theorem say? It says sine of x, right, is equal to the sum, k equals 0 to infinity, of the kth derivative of f evaluated at 3 over k factorial, right, times x minus 3 to the k power. This is, the Taylor series, the Taylor theorem, right? Which, by the way, I have not justified. Just take my word for it for the moment, okay? I mean, we motivated this last time, why that should be true, right? The derivatives of the function have to match the coefficients of the series in this way. That we've justified. What we haven't shown is that it actually has to match the function. That's a subtle business. All right. So then what? Let me advocate, we could look at this as what? This is really f of, say, 4j of 3 is equal to sine of 3, right? This is saying f of 4j plus 1 of 3 is equal to cosine 3. This is saying f of the 4j plus second derivative at 3 is equal to minus sine 3. And this is saying f of 4j plus 3 at 3 is equal to minus cosine 3. You could put these two things together, and you could say that, in fact, f of 2k of 3 is equal to sine of 3 times minus 1 to the k. I can lump those two cases together. Even derivatives give me sine of 3 times plus or minus 1, right? Am I right? My formula work? I don't know. If I put k equals to like, Oh, I'm pattern matching. There's no steps. Just thinking. I could be wrong. So here, I'm saying that 4j, so here I've got 4j is equal to 2k, and down here I've got 4j plus 2, I'm saying is equal to, well, that's 2 times what? 2 times j plus 1, right? Let's see here. I mean, that's an identity. Oh, but I mean 2j, thank you. Man. 2j, is it, what'd you say? 2, what'd you say again?
The 2j in that in the parentheses equal to k.
2j equals to k. Yeah, let's do that. Understand my thinking. I guess I'd like to understand my thinking too. Don't worry, nothing was lost. I'm recreating it more cleanly. It's for the best. The 2j is equal to k. Okay. So this is like, what is this? This is what? 2k, right? And this would be 2k plus 1. Yeah. Well, I don't know. Like I said, I really shouldn't try to. If I try to explain this, I'm just going to make it confusing. The point is, you've got these. What's that? Wait, what do you want from me? I mean, it's a hard problem to do this way. This loops. So if you keep going 4 more, and 4 more, and 4 more, you're still at sine. It goes back to sine every 4. It goes to cosine every 4. It goes to minus sine every 4. There's a fourplicity here. Okay, not a word. But so the point is, the even values, right? Even values are either what? 0, 4, 8, 12, and so forth. Or they're 2, 6, 10, 14, and so forth, right? These give us sine of 3. These give us minus sine of 3, right? This formula does both of those at once. Yes?
Doesn't the negative 1 to the k throw out though?
Yeah. Like,
Because you don't have every value of k. Should it be like something else?
Does it work?
Wouldn't it be always just sine of 3?
When k equals to 0, it gives you sine of 3. When k equals to 2, it gives you sine of 3. When k equals to 3, it gives you what? Which it should, because k equals to 3 is this guy.
So what about the
This is k equals to 4. Yes. All right. Likewise, the cosines, right? You've got yourself a 1, 5, 9. This seems to be more successful with you guys, enumerating this way, so forth. That gives us what? Cosine 3, right? And the what? 3, 7, 11, 15, and so forth gives us minus cosine of 3. If I want both of these patterns in one foul swooping formula, that would be f of 2k plus 1 at 3 is equal to what? How about minus 1 to the k times the cosine of 3? Agree? All right, so this, I really shouldn't use k. Let me use something other than k here. Let's say, let me go back here and make this k into an n, just to kind of free your mind. All right? So n is either even or odd, right? So I can break this series into a sum of even terms and odd terms. And I found the value for the even coefficient and for the odd coefficient almost there and there, right? I say almost because I also have to do what? Taylor's series, I have to divide by n factorial, right? So here it is. This is the sum. K equals 0 to infinity. What was it? Sine 3, yeah, sine 3, sine of 3 minus 1 to the k divided by k factorial, x minus 3 to the k, plus the sum k equals 0 to infinity of cosine of 3 minus 1 to the k over k factorial x minus 3 to the k. What's the question? So what I'm doing is
Are you including x for the sine 3 but not for the x minus 3? I'm just wondering if x has a value in this.
No, x is a variable. X could be anything. X is a variable here.
Okay.
Any real number. 3 is the center. We're trying to find the power series expansion of f of x equals sine x about the point 3. This was a worthwhile exercise for us to go through. If nothing else, to expose you to this world of thinking. You're going to have to do these kinds of things in problems, right? That's the kind of computation which is probably new to you here, right? So I'm trying to expose you to some notational ideas that are helpful beyond just listing things, right? Understanding that when you have a fourplicity, you can break things into like 4j plus 1, 4j plus 2, 4j plus 3, and these are general formulas, right? But 4j plus 2 and 4j plus and just 4j, those together give you all the even terms, right? And 4j plus 1 and 4j plus 3, those together give you all the odd terms. So if there's some kind of nice pattern between those, you might be able to put those together also. I mean, so before I erase this, anybody have any questions about this one? This particular homework problem? I don't know if we talked about this already or not. This is 12.4, number 12. They asked me earlier how to do it. I basically told them, I look at this, I go, well, that's really, if you look at it, what's dominant is the k and the k cubed, right? This is essentially a p equals 2 series. So that tells me intuitively that must converge. Then I go about, I set out to try to prove it. So my first thought was limit comparison. That seems like a nice, not too hard to think about way to do it. And I'm going to compare to the p equals 2 series, which we know converges, right? And so we take the quotient a sub k over b sub k, which is this. You do algebra, you get to here. That goes to 2. Well, 2 is a positive quantity. So the limit comparison test then says that that the series that's given converges if and only if the p equals 2 series converges. Well, the p equals 2 series does converge. Consequently, the given series converges by the limit comparison test. Now, there is some fine print. I have to be sure that I'm looking at series with positive terms, right, in order to compare them. But that's the case here, so we're fine. The other way you could do this would just be a straight up basic comparison, right? Because if you look at this, right, you can drop either of these things from the denominator and make it smaller, but a wise choice would be to drop the root. Because then you've got this plus that over k cubed, right? Which is 2 over k squared plus 1 over k to the 5 halves. Both of these are terms which give you convergent series. So that converges by p equals 2. That converges by p equals 5 halves. Consequently, we have this, the series formed from this term converges. Hence, by basic comparison, this converges. So you could either go limit comparison or basic comparison on this problem. Up to you. I don't know. Can I erase? I just wanted to share with you that thought process because, you know, this is a very nice, relatively simple homework problem, you know? I mean, it's not the most simple homework problem, right? On first glance, it's kind of terrifying, isn't it? But after you start trying to use the tools which we have developed in here to solve it, it's not that bad. There are much worse problems in your homework, right? Oh. All right, so part of what I'm trying to get across to you here is the Taylor series is easy to understand. This is actually very easy to understand, right? What does this say? You differentiate the function, you plug in the value, you write it out. Now, to actually come to the full story, it's rather involved for some functions, right? But the actual result is very easy to understand. Most of you understand that by the time the test happens, and you glom onto it too much. Because it's not always the best way to find a series. Like here, I would argue what we did in terms of differentiating then integrating was better. This one would have been easier. If we'd used Taylor series directly, we just differentiate and plug in 0, it would have been pretty fast. Right? Can you see that? Should I write it out? So like f prime of 0 is 1, f prime prime of 0 is minus 1, f prime 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 of 0 is 1, well 2 rather. And you keep going here, eventually you'll see the pattern. The nth derivative evaluated at 0 is exactly minus 1 to the n plus 1 times n factorial. So therefore, if you look at nth derivative evaluated at 0, divided by n factorial, what that gives you is minus 1 to the n plus 1. But that's exactly, oh, I've missed something here somewhere. Oh, it's not quite n factorial, is it? What is it? What's the pattern here? When we're at 3, we have 2 times 1, right? Yeah, n minus 1 factorial. So when you take n minus 1 over n factorial, you get minus 1 to the n plus 1 over n, which is exactly what we wrote over here with k. So yeah, fair enough, you caught me. Taylor series is easier in that example than geometric series technique. You caught me. Right? Fine. I admit. Or is it just that we already went through the example, so it seems easier the second time? I don't know. But there's another way to do this one I want to show you. So we've got sine of x, right? I want to recenter it at 3. Remember what I showed you guys last time? Adding 0? Remember adding 0? So centering at 3 means they don't want x. X is not natural. What's natural is x minus 3, right? So I do x minus 3, and then, but to be fair, what do I have to do? I have to add 3, right? But this is like A, this is like B, and we know that sine of A plus B is what? Sine A cos B plus sine B cos A, or however you want to write it. In other words, it is the cosine of 3 times the sine of x minus 3 plus the sine of 3 times the cosine of x minus 3. I'm not trying to match the A and B up precisely, okay? I may have shuffled the terms around, but that's the idea. And then you substitute. cosine 3 and sine 3 are constants, so you could bring them inside the sums like they were over here if you want. Or you could leave them outside. I like this as an answer. I mean, okay, fine, it's not technically a power series yet. Supposed to write it like this. Fine, fine, fine. Hope you guys are happy. Oh, yes. I hope not. Ah, that's because this was dumb. You guys didn't correct me. Right, I'm supposed to have, yeah. Well, this was 2k, right? Sorry, let me make the correction in red. That was supposed to be 2k and 2k, because that was with the sine, right? With the 2k. And the odd terms over here, let me make the corrections in blue. There we go. I should have already done that on the basis of star and star star, right? What? Okay, I'll allow it. What?
You just plug it into the equation on the memorize. Sine u equals sine of 3. Is that what that's for? No.
I am asking to find the power series for sine centered at 3. Not just sine of 3. Of course, somewhat sarcastically, if you plug in 3 into this, it's fun. Plug in 3. Sine of 3, yeah. That's 0, and that's 0. For any positive power, only the constant term remains. What's the constant term? Over here, j equals to 0. Sine of 3. I mean, so sine of 3 is equal to sine of 3. Woohoo! True, yes. Now, of course, if you actually want to calculate numerically the value of sine 3, yeah, this is the way to do it. You plug it over here. Yeah. Anyway, I'll shut up. Other questions? Now, okay, so, you know, this was a relatively innocuous problem. What if I tell you now all of a sudden, this method of thinking, no. Not if you want to find the whole thing, right? If you want to find the whole thing, it's still a pain, but you just do this, you know, x minus pi plus pi times the cosine of x minus pi plus pi squared. Dot, 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 use that stuff, make substitutions, multiply series. It's a pain, but you'll actually get to an answer. Whereas with this, trying to see the pattern in the chaos, you'll probably get lost. Anyway, I'm now showing you second order computational techniques, so I probably should kind of stop and do more geometric series stuff. But anyway, that's all for today. You guys have questions about your homework? In the time that remains? Oh, I was supposed to look at number 26 from 12.4 and 26 from 12.5. Maybe you guys also have questions about those? Yes, no, maybe so. Can somebody tell me what those problems are? Let me steal your book if you don't mind. Thanks. I walked up here and I was feeling light. My feet, it was like I was just light on my feet, and we got up here and I'm like, oh, I don't have my book. That's why it was such a pleasant walk. Let's see here. So the earlier section has requested we look at 26 of 12.4. We'll try that one on for size here, see what we get. Maybe you guys can tell me how to do it. 26 is, oh, this one's fine. This is k factorial over k to the k. This is straight up ratio test, yo. Yo, yo, yo. What, k factorial over k to the k? This ain't bad. Didn't I work this out? Oh, maybe it was in office hours or something. So ratio test, a sub k plus 1 divided by a sub k equals to what? K plus 1 factorial divided by k plus 1 to the k plus 1 times k to the k divided by k factorial. Simplify this. We've got k plus 1 times k factorial divided by k plus 1 times k plus 1 to the k. And then over here, of course, I still have k to the k over k factorial, right? So stuff cancels. Ah! And we're left with k over k plus 1 to the k power, which is otherwise known as k plus 1 minus 1 over k plus 1 to the k power, aka 1 minus 1 over k plus 1 to the k power. Which is indeterminate type, right? So you'll have to figure it out. But I do believe, yes, sir.
Can you do 1 over k plus 1 over k? Just put it in the denominator, switch it around, and make it 1.
Ah, yeah. Sure. If you want to. Yeah, it's definitely going to be, I think that's e to the minus, that goes e to the minus 1. I believe when you work out the details, this should be able to show this goes to e to the minus 1. Consequently, it converges, which is intuitively clear because k to the k beats k factorial, right? If you flip this over, the ratio test, instead of going to 1 over e, goes to e. I know I've done this before. I'm not sure. This example exactly, something awful lot like it. Yeah.
Can you explain how you
Definition of the factorial function is that n factorial is n times n minus 1 factorial. So if I have like k plus 1 factorial, I can rewrite that as k plus 1 times k factorial. That's your go-to algebraic step for the factorial function. That's like, in some sense, that's the definition of the factorial, which we make recursively. All right, number 26 from 12.5 was what? Ooh, scary. This is very scary. This is 12.4, number 26. Yeah, I know, like, there's something up with 26 today with the other section, right? Here we got ourselves a cosine pi k over k. And I feel like this is from, well, I don't think the bound is given. Obviously, it doesn't start at 0, right? What is this? Is it, remember that test or quiz where we had this issue? What's cosine of, or was it sine? I don't know. What is cosine of pi k? It is between 1 and -1, that's true. It's actually even better than that. It's not 0. It is either 1 or -1. In fact, this is -1 to the k. So I guess we can take 1 to infinity if you want. I'm going to take 2 to infinity for my convenience. Why would I do that? See, because then this is 1/2 minus 1/3 plus 1/4 minus 1/5, da-da-da. In other words, this converges by what? The alternating series test with b sub k equals to 1 over k, which goes to 0, and b sub k is positive, decreasing, and what? Has limit 0, yeah. That's clear for this one. I don't think I need to show work for that. I would be not too upset with you if you just said it's clear that b sub k is positive and decreasing, because it's 1 over k. Okay? Yeah. So you guys have a question? Another problem? It was recommended to me, and I'll share this advice with you guys. There's a very nice paragraph at the end of section 12.4. There's a summary on convergence tests and page 596, which kind of gives you some kind of heuristic on when to use root test, when to use ratio test, and a few other sort of just generic pieces of advice. That's kind of nice. At some point, I'll attempt to draw a flow chart or something like a flow chart to try to illustrate the big picture of what we're doing. We don't have time today, but someday I'll try to do that. You guys need to work a bunch of problems before you understand the chart, though. If I try to write the chart at the start, if I try to give you the big picture of what we're doing at the start of all this, it won't make a bit of sense. You can't understand what we're doing until you understand each one of the tests we're using. Only once you have learned the players in the game can you understand the game, So, or something like that, I don't know. Yes, homework is due Tuesday. That is true. There is relatively little homework due Tuesday, I think, so. But it is due Tuesday, because we need to get this convergence stuff behind us. So try to figure it out, do your best, and then we go on. Any questions about the homework? No? What's that? That's it. All right, well, that's it.